Good afternoon, folks. How are you today? So we are in lecture number 5. We just finished talking about Newton-Raphson method to solve for root of an equation of the form fx is equal to 0. So now we are going to talk about the next non-bracketing method called the secant method. So secant method is basically a minor variation on Newton-Raphson method. So let's take a look at our function. And let's say it crosses the x-axis here. So we are after this root. So secant method needs two initial guesses. Let's call them x1 and x2. So let's say we have x1 here. So we compute f1. And let's say x2 is here. Now we don't need to bracket the root. Both the points could be one side, like you see in this particular example where we can do extrapolation. But the one I'm drawing on the pad is this particular diagram. So we evaluate the function and it is f2. So then what we do is we connect both of these points and that becomes our next guess, or x new. Okay, so let's see how we can get x next. Usually we always formulate in terms of finding a delta x. So what we'll say is x next is x2 minus delta x from this figure. So let's look at our triangles. So this small triangle, let's say if this angle is theta, then this angle is theta. So we can write an equation for tangent of theta. So our tangent of theta would be, if we look at this small triangle, it'll be f2 divided by x2 minus x next. If we look at this big triangle, it'll be f2 minus f1. That'll be the height of this triangle, x2 minus x1. And you can see this quantity is delta x. So we can write delta x therefore is f2 over f2 minus f1 divided by, multiplied by x2 minus x1. So we take this here, we just are doing the diagonal exchanges. So this becomes our delta x from secant method. Okay. So all we know is x new is x2 minus delta x. So if you'll notice this particular part is something like f2 prime. So f2 prime is roughly f2 minus f1 over x2 minus x1. So you can see approximately this is f2 over f2 prime, very similar to Newton's method. Okay, so now let's implement it. For our example problem. So remember our example problem was fx is equal to x squared minus 5 is equal to 0. We're trying to find square root of 5. So let's make a table. So we have iteration number. We start with x1, x2, we'll find f1, we'll find f2, then we'll calculate delta x, and we will get x new. So we know our root is between 1 and 5. So let's choose x1 to be 5, x2 to be 1. So at x is equal to 5, our function would be 20. At x is equal to 1, it'll be minus 4. And our formula, remember, was, let me write it on a side somewhere, delta x was f2 times x2 minus x1 over f2 minus f1. Okay, so we use our calculator. And we have f2, which is negative 4, times x2 minus x1, which is also negative 4, divided by f2 minus f1, which is negative 24. And we will get 0.6667. We'll keep 4 digits only. And we are going to subtract 1 minus delta x. So we will get 1.6667. So now what we do is, when we go to the second iteration, this 1, which was x2, becomes our x1, and this x new becomes our x2. So we have our function value, and we calculate new function value at 1.6667. So I punch in 1.6667 square minus 5, and I'll get minus 2.2221. So we keep going this way. You should really take a calculator and follow along. See if you get these values yourself, because you'll be doing it on your tests and final exams, similar problem. So on the next iteration, our new guess comes out to be 2.5. Notice that the magnitude of delta x increased slightly. Now on the next iteration, delta x dropped quite a bit, almost 1/3, dropped by a factor of 10 almost, another factor of 10, actually 100, I should say. And you can see now, keeping 4 digits, we cannot improve further. But delta x dropped quite a bit. And we get 4-digit match after about 5 iterations. So you may remember, in Newton-Raphson method, we converged in 3 iterations. Here it took about 5, but remember, we are also keeping only 4 digits. So once we come here, we can say our root is approximately 2.2344 plus minus this 0.0002. So secant method is really where we are just approximating the derivative instead of using analytical derivative. So convergence behavior is similar to that of Newton-Raphson method, meaning that we may have problems if either first derivative or second derivative or both are 0 or nearly 0 near the root. This method is very useful when f prime is not available or is very expensive to compute or derive. So often we don't know the function analytically. So often we have to use, therefore, secant method. We cannot use Newton-Raphson method. Since we are using approximate derivative, the convergence rate is not as good as Newton-Raphson method. So for Newton-Raphson method, it was quadratic. So convergence rate here is slightly less than quadratic. So it is between linear and quadratic. So we call it superlinear. Okay, our next method is fixed point iteration method. So what we do is we are given the equation of the form fx is equal to 0. We transform it to the form gx is equal to x. So if this equation has a solution, meaning if f has a root, so if alpha is root of f, then this alpha will also satisfy this equation. That means g alpha would be equal to alpha. Then what we do is we say alpha is fixed point of g. So instead of finding root of a function, we try to find therefore fixed point of a function g. Now, of course, there are many ways to do this transformation. And some ways may be much better than others. So let's see graphically how this method works. So we make a plot of x and gx. And this is our line, y is equal to x. Then we plot g of x. So this is our line when y-axis is g of x. So g of x becomes x at this point. So this is the fixed point of g of x. So this is what we want. So notice, suppose we start with the initial guess, x1. So this method needs a function gx and initial guess x. Let's call it x1. So what we do is we evaluate g1, and this g1 becomes x2. So now we evaluate g2, it becomes x3. And you can see we just go down this steps and converge towards the root. Let's see another particular case. So again, we have y is equal to x, 45-degree line. And then we plot our y is equal to g of x. So this is now our fixed point. So let's see, we start with the initial guess, x1. So we compute g1. g1 becomes x2. We compute g2, which becomes x3. And then we compute g3. So you can see that we are therefore spiraling inwards towards the root. So we started with x1, x2, x3, and so on and so forth. So let's see how this works for our example problem. So our function is x squared minus 5 is equal to 0. So we need to transform this into a form gx is equal to x. I'm going to do it in a strange way. What I'm going to do is I'm going to subtract both sides of the equation from 2x squared. So I'll do 2x squared minus x squared minus 5 is 2x squared minus 0. So I've subtracted both sides from 2x squared. So we will get x squared plus 5 is equal to 2x squared. And now I'm going to divide both sides by 2x. So I'll get x squared plus 5 over 2x is equal to x. So that means I have got this form gx is equal to x form. So let's make our table again. Iteration number, we have x, we compute gx. So let's say our initial guess we start with is 5. So we compute g of x at 5. So we will do 5 square plus 5 divided by 2 times 5, and we will get 3. So you might like to calculate along with me. Second iteration, this becomes our new guess. We compute, so now this time 3 square plus 5 divide by 2 times 3, and we will get 2.333. And so on and so forth you will go. So you can see from 5 we got 3, from 3 we got 2.333, and then so on and so forth we will go. And you can see right after about 5 iterations or so, we have gotten 5 correct decimal digits. And of course, I've shown you how we can implement it in a spreadsheet here. So it turns out that fixed point iteration method also has convergence issues. So consider this one. So here is our y is equal to x, and here is our function g of x. So we are interested in this fixed point. So we start with the initial guess, and you can see right away, we evaluate the function, that becomes our next x. Evaluate the function, that becomes our next x. We are diverging away. So even though we started very close to the fixed point, we diverge away. Another example. So here is our 45-degree line. Here is our function g of x. We start with the initial guess, compute the function, next x, compute the function, next x, compute the function, and you can see we are spiraling away from the fixed point. So fixed point method convergence conditions are that fixed point method converges if the magnitude of g prime x is always less than equal to 1 in our search neighborhood. So whenever we are searching for the fixed point, if in the neighborhood this derivative remains less than 1 in magnitude, then we are okay. We are guaranteed to converge. And you can see this is what was happening here. Here you can see the slope was greater than the 45-degree line. Here negative slope, but you can see if the angle is more than 45 degrees. So since this angle is more than 45 degrees, we are diverging away. Now it turns out, so the convergence rate is superlinear. Now it turns out that the fixed point iteration method is identical to Newton-Raphson method if we choose our function g such that it is x minus function over function prime. So remember, we had a form f is equal to 0. So that is the form f is equal to 0 is where that f comes from. We wanted to transform it into the form g is equal to x. So that is this function g. So now you may see why I did my transformation in a very strange way. Suppose I had my function x squared minus 5. I take its derivative, 2x. So my Newton-Raphson method would say x nu is x minus f over f prime. So if I substitute x squared minus 5 over 2x, simplify it, 2x squared minus x squared minus 5 over 2x. So this will be x squared plus 5 over 2x. And that is our g of x. So that is what we did here exactly. So we took this function, did Newton-Raphson method on it, we would have been basically implementing fixed iteration method. So it turns out, you may recall, I started the whole example by saying, how does your square root key work? So you're given an a, you want to find square root of a. So what is happening is, think of the chip behind your square root key as follows. You feed in a, and it uses this a as a initial guess 2. So this, it feeds it as x. And then what it does is, remember, g of x was x squared plus a over 5x, over 2x, sorry, 2x, not 5. So it computes this function g of x, and that becomes, remember, your x nu, and that is fed back here. So it just keeps on iterating certain number of times that we know this function would converge in and spits out the root. So if you had, for instance, a calculator from 1970s, maybe you can find such a calculator in maybe your grandpa or grandma's kitchen table, you may see that those calculators were so slow that when you punched in 5 and the square root key, the digits flashed as it was iterating. So it was, the flashing digits were these x nu, and about 10 iterations or so, it would stop and flash you the square root value. Okay, so we did a discussion about significant digits, correct decimal digits, when we talked about convergence criteria. So I want to mention that these concepts are in context of this course, and they are different from traditional definitions. So let's again formally say for this course, how do we count correct decimal digits? So we have a number, let's say xxx dot xxx. So we start counting from the decimal point. So if we count towards right, we go positive. So this is our first digit, second digit, third digit. So this is our positive direction. This is our negative direction. So if this was 1, the digit to the left of decimal point is 0, -1, -2. So if this was the last digit that was correct, we will say we have -2 correct decimal digits. So CDDs can be positive, negative, or 0 integer values. Okay. Then we said leading zeros. If there are any leading zeros, we ignore them because they are not significant. But trailing zeros, we count them in if they are significant. So let's look at correct decimal digits. So here I've taken value of pi, you can see approximated, and I have stated it in different unit systems. All the digits shown are correct. So here we have 4 correct decimal digits, 5 correct decimal digits. And now notice if there are these leading zeros, if they are beyond decimal point, we count them in. So here is 3, 6, 8 correct decimal digits. Here, imagine as if you have a dot. So you have a dot, 31400 dot XXX. So notice this digit is correct. So we count that as 0 digit. So we say CDD is equal to 0 because this digit is correct. So here is another example, 031400. So we get 6. All right. In counting significant digits, we ignore the location of the decimal point. We ignore all leading zeros. Trailing zeros, we count if they are correct. And often it is easier to count significant digits if we express the value in floating point notations, because significant digits are not dependent on magnitude of the value. We can put decimal point wherever we like. So here are all the same numbers. I've expressed them in floating point notation. So from floating point notation, we get the magnitude of the numbers. So that is listed here. These are the exponents of 10. And we have the number of CDDs from the previous table, right? And our formula was, remember, significant digit is CDD plus M. We can say M is SD minus CDD. So whatever way we use the formula, you can see all of these significant digits, this formula matches every row, basically. Now let's look at, suppose our diameter was pi in millimeters. So we can express this diameter pi millimeters in different units. So here is meters, kilometers, microns, nanometers, picometers, etc. So here is the fractional way I've stated it. Here is floating point notation. Notice in all of these, I'm keeping 5 significant digits, 5 significant digits. Here are the magnitudes. So you can see significant digits does not change when I change the unit, but number of correct decimal digit changes when I change the units. So CDD is unit dependent. Now so that was all mathematical definitions. Now let's look at our convergence criteria. When we use the absolute criteria, we said we guarantee exact number of digits. But when we use the relative criteria, all we are saying is we will have at least that many significant digits. So let's suppose here is the results from our numerical methods for a given problem. Three different results. Okay, so here is z plus minus delta z. So let's express delta z in floating point notation. So once we have in floating point notation, we can easily determine correct number of decimal digits. So correct number of decimal digits here is -2. Since this number is more than 0.5, correct number of decimal digit here is 5 only, not 6. This is less than 0.5, so 3 correct decimal digits. So 2, 5, 3. Now let's look at our delta z over z. So these are the values. So we have at least three significant digits here, at least two significant digits here, and at least four significant digits here. So here our math formula, this plus this is this, matches. M plus CDD matches. But notice here, we should have 5 CDD, but our formula is only promising only 4, minimum 4. So here, notice our mathematical equality is not met. Okay, so let's see how computers work. So when we think about numbers, we have two kinds. We have integers and we have real numbers. Now it turns out that integers we can specify exactly. So we say we have infinite precision or there is no loss in precision. Whereas real values, when we work with it, we cannot store them exactly. So they are imprecise. So therefore, we will run into precision problems whenever we work with real values. So of course, we can work with different number bases. Human beings, we work in base 10 decimal. So we use 10 digits. Machines work in binary system. So they have just on, off, or 0, 1, 2 digits. So when we work in different languages such as Visual Basic or C, we can store our variables in different forms. So we can have a short integer, we can have a long integer, or we can have a long integer. And the way they are stored is typically we say that short one takes 2 bytes, long one is 4 bytes. So a typical word length, standard word length is 4 bytes. And then we can have a long 8 bytes. So what does this mean? So let's start with a bit first of all. So when we have a binary bit, a binary bit can only take form 0 or 1. Then if we combine 8 bits, we form a byte. So 8 binary bit is 1 binary byte. So of course, if we have only 1 bit, we can have only 2 possible combinations. If you have 2 bits, we can have 0, 0, 0, 1, 1, 0, 1, 1. We can have 4 combinations, 2 to the power 2. So generally, if we have n bits, we have 2 to the power n bit patterns, unique bit patterns. So what we can do is, we can say, therefore, half of them are negative. So we can represent half of those patterns as negative integers, other half positive. But we still need one pattern to represent 0. So to represent 0, what we do is we take one of the patterns from the positive side and borrow it to represent 0. So therefore, our integer range that we can represent in general would be, we have beta to the power n patterns, base to the power n patterns. Half of them are negative, other half is positive. We are borrowing one of the patterns from positive side to represent 0. So this is what is called underflow limit. This is what is called overflow limit. So you can see here in this table, 2 bytes means 16 binary bits. So we have 2 to the power 16 combinations, that's 65,000 combinations. So half of them, roughly minus 32,000, are negative integers. Other half are positive integers. Notice we have borrowed 1 from the positive side to represent 0. So underflow, overflow limit. So same way you will go minus beta over 2 to plus beta over 2 minus 1. So when we are representing a standard integer, we can go from approximately minus 2 billion to plus 2 billion. Now when we go to a long integer, a 8-byte integer, we can go something like from minus 10 to the power 18 to plus 10 to the power 18. Now the key idea in integers is, since we can store integers perfectly, there's no loss in precision. When we do arithmetic with it, that is also precise. So when we take A and B, if they are both integers, and we do all our arithmetic, A minus multiply, and we get a result, result is also an integer. And this is exact answer. So this, there is no loss in precision. The only problem may be overflow or underflow limit. Okay, so now let's see when we are storing real values. When we want to store real values, let's say z, first we stated in this z in floating point notation. So we will write it as plus minus 0 dot xxxx times beta to the power some q. So therefore what we need to do is, we need to store, first of all, we need to store sign of the mantissa. Then we need to store all the mantissa digits. Let's say these are n of these. So we have n significant digits in our number. Then, of course, we have base beta, but we don't need to store, because for every machine this is fixed. For every real value we store, it is fixed. But we also need to store this exponent q. And remember, q is always an integer, positive, negative, or 0. So just like integers, we have a variety of types of real values. So we have single precision numbers, which are 4 bytes, double precision, 8 bytes, quad precision, 16 bytes. So 4 bytes is 32 bits, so 8 bits per byte. So you can see we're just multiplying by 8 here. So what we do is, for binary bits, we take 1 bit, which has 2 patterns, to represent our mantissa sign. So often Mentessa is 1 bit. Then to store n bits, in case of single precision, what we do is we store 23 bits of Mentessa digits. They are 0 or 1. Remember, binary digits only. So if we had 32 bits available to us, we have already taken care of 24. All that remains is 8 bits that we can use for exponent. So when we have a 32-bit real value, and we can use 8 bits for storing this integer q, our range of the integer q would be, remember, 2 to the power 8 over 2 positive. We borrow 1 from the positive side. 2 to the power 8 over 2 on the negative side. So it turns out this is minus 128. This is plus 127. So we get an exponent range from minus 128 to plus 127. So this is our Q min and this is our Q max. So now when we think about our overflow limit for real values, so what is the largest magnitude we can represent? Well, all these Mentessa digits can be all ones. And our largest exponent is Qmax. So think of this as half plus a quarter plus an eighth, on and on. So this all is nearly 1 in any base. So therefore, our overflow limit is beta to the power Qmax. Okay, let's look at underflow. Now, our first digit must be non-zero. So the smallest it can be is 1. All the rest of the digits can be 0 times beta to the power Q min. So this is like 1 over 2. So this is like 1 over beta. So therefore, we have a formula for underflow, which is beta to the power Q min minus 1. So let's calculate this using a calculator. So for single precision, our formula for overflow is beta to the Qmax. Well, for our problem, beta is 2, Qmax is 127. So this number is 1.7 times 10 to the power 38 plus. Let's look at underflow. Which is beta to the Q min minus 1. So we'll have 2 to the minus 128 minus 1. This comes out to roughly 0.15 times 10 to the minus 38. So you can see that in single precision, we can store and represent numbers in the range from 10 to the minus 38 to 10 to the power plus 38. You should attempt to calculate this and this in the next two columns on your own. Then our last thing is how many significant digits can we store? So instead of talking about significant digits, what it talks about is machine precision. So what is our machine precision? Machine precision is what is our relative error bound. So this relative error bound is beta to the power 1 minus n. So in our case, what we do is we compare it to, we assume machine is rounding machine, even though real machines are actually truncating machines. We compare it to beta 10 to the minus SD, right? Okay, so let's see for our example. So this is number of Mentessa digits. So in our case, 2 to the power 1 minus, remember we have 23 Mentessa bits here. So 1 minus 23. So we calculate this, 2 to the power minus 22. So we will get 0.24 times 10 to the minus 6. So notice, therefore, we have at least 6 significant digits in decimal base, but could have maybe 7. So we have 6 to 7 decimal digits. But remember, this one we are calling correct decimal. This is like decimal means base 10. So we are talking 6 base 10 significant digits, 15 base 10 significant digits. Okay, I've just included this chart just for your knowledge because we have been using all these terms, micro, nano, pico, so you need to remember what they mean. Now, in terms of Excel, Excel works in double precision. So you will see it can give you 15 significant digits. Its underflow is like 10 to the minus 308. Overflow is 10 to the power 307. So these are kind of the final values they can calculate. Just some other things that I copied from the specs.